Well, let's start the seminar. So I'm happy to present Alexander Poshakinskii, a brilliant young researcher from the Institute of Photonic Sciences in Spain, Barcelona, who has originally graduated from the University Institute of Russian Academy of Sciences in St. Petersburg, and who will present an interesting story about a persistent spin pattern in solid-state systems.
Merci beaucoup, Dima. Dima m'a dit qu'il faut absolument que je parle un peu français, donc voilà. Voilà. Je vais parler aujourd'hui de la propriété de spin dans une gaz d'électrons bidimensionnel. La première moitié de ma présentation va être consacrée à l'introduction. Je vais décrire les propriétés de spin, surtout l'interaction spin-orbite, qui contrôle les propriétés de spin et qui est surtout responsable de la réaction de spin. Et ensuite, je vais présenter les méthodes existantes pour supprimer cette réaction, soit en ajustant précisément les paramètres des spin-orbites, soit en limitant le mouvement des électrons à un canal unidimensionnel. Et finalement, je vais présenter une nouvelle méthode pour supprimer la réaction de spin, c'est-à-dire qui ne limite le mouvement des électrons, qui permet la diffusion bidimensionnelle et pour laquelle il n'est pas besoin d'ajuster les paramètres de spin orbite qui peut être réalisé pour quelconque paramètre. Et bon, c'est tout pour mon français. Et je vais continuer en anglais.
Thank you.
Okay, so if we consider two-dimensional electron gas of electrons, for example, in quantum bells, gallium arsenide quantum bells, its spin properties are determined by spin-orbit interaction. And the Hamiltonian of electrons looks like something shown here. So we have a first term, which is just the usual kinetic energy, and then there is a second term which depends on electron spins. So here there is Pauli matrix sigma. And if we plot the corresponding dispersion of electrons, it looks like something shown here. We have two electron subbands with opposite spin orientations, which are split by the value, which is crucially depends on the electron's wave vector. And you can think about this splitting as a sort of effective magnetic field, which leads to this kind of Zeeman splitting. But again, this Zeeman splitting depends on the wave vector. Then, if we consider evolution of the electron and its spin in the structure with this kind of spin-orbit interaction in virtually any quantum well, it looks like something shown here. We have an electron, it moves in space with some wave vector, with some velocity, and at the same time its spin rotates around this effective magnetic field. So electron moves, spin rotates, and as a result we have in space this kind of pattern of alternating spin with coordinate. But of course this kind of nice pattern occurs only while the electron is moving ballistically. As soon as electron gets scattered, it in general no longer holds. And for experimental setups, almost all quantum wells, the most relevant regime of electron dynamics is the diffusive regime. So electron encounters many scatters until its spin has rotated on a significant angle. Okay, so this is what is more relevant. So in real space we have a Brownian motion of the electron, and this Brownian motion, the diffusion, is described by the coefficient d, which is just the velocity of electron squared times the scattering time tau. And now, simultaneously with this motion in real space, electron spin rotates. So on each part of the trajectory, electron spin rotates around a different direction corresponding to this particular direction of motion. And as a result, we can look at the electron spin as a vector which rotates in a fluctuating effective magnetic field. So if we start from spin up, spin exhibits these random rotations, and we can think about it also as a kind of diffusion, but now on a block sphere. So we start from the North Pole, and then the spin distribution spreads around the sphere. And similarly to the electron motion in real space, we can introduce a kind of diffusion coefficient, but now on a sphere, and it will be similarly the angular velocity, this spin precession frequency omega squared, times the same scattering time. And of course, when the spin distribution has diffused over the whole block sphere, that means that effectively the average spin is zero. So the spin has disappeared. This is spin relaxation. This is mechanism proposed by Dyakonov and Perret, and which is the dominant mechanism in quantum wells. So looking at this picture, it seems that all was unavoidable if we have a random motion of electron in real space that leads to random spin precession, and spin relaxation is almost inevitable. But there are ways, there are approaches how to suppress the spin relaxation, and I will now describe the first of them, which consists in the fine-tuning of the spin orbit parameters. And for this, I first need to introduce how exactly this effective magnetic field looks like. So I will focus on this quantum wells drawn in a 001 direction. There, the spin orbit field consists of two terms. There is a Rashba term, alpha, and there is a Birchhaus term, beta. Here on this figure, I show their distribution on a Fermi circle, how this effective magnetic field depends on the electron wave vector. So, in principle, both of them are in some sense tunable. The Birchhaus term is determined by the bulk inversions asymmetry, that is the thin blend structure of the bulk crystal, and Rashba term is determined by structure inversion asymmetry. That means the kind of built-in electric field in the structure, kind of asymmetry in the quantum well. Okay, so they look like this. And if we add them up in realistic structures, both of them are present. In general case, we obtain something like shown here. So the spin distribution, the spin orbit field distribution on the Fermi circle is anisotropic, and nothing particular happens. But the interesting thing happens if we tune these parameters in such a way that their amplitude match each other. Then the distribution of effective field on the Fermi circle looks like here. So it is directed along x and depends only on ky component. And this is what is called a persistent spin helix regime, and I will now explain why. So in this particular regime, the electron spin rotates always around the same direction, around the x direction. Yeah? And then we can easily write the equation for this rotation. So the rotation angle, phi, its derivative, is given by this frequency of precession in spin orbit field, and this frequency of precession in spin orbit field is proportional to ky in this regime. And ky is basically the electron velocity. And this simple equation is easily integrated, and we get a new integral of motion. It says that the electron spin rotation angle phi is proportional to electron displacement. So in contrast to what I was saying in the beginning, here in this particular regime, whatever trajectory electron chooses to move from one point to another, it always exhibits the same rotation. Its spin always exhibits the same rotation. In general, it's not true. In general, the rotation angle of the spin depends on the trajectory, but in this particular regime, this dependence disappears. And this is very beneficial for experimental observation of this rotation in spin orbit field. Here I show the typical experiment performed to detect this spin rotation with spatial resolution. It is performed in the following way. So we have a pump, we have two focused optical beams, pump and probe. So by a pump beam, which is circular polarized, local electron spins are excited. And then by a probe beam, which is linearly polarized, we occur rotation, the spin distribution in the whole plane can be measured. So what is done, it is the position of the pump and probe are scanned one with respect to the other, and the maps of spin distribution and different moments of time can be obtained. And this kind of experiment is shown here. So we start with some spins up in the center. This red color corresponds to spin up. Then time goes, and the oscillations of spin in space rise. So the spins move from this central spot to the sides. They start to precess. This precession depends only on this y coordinate, and we see this nice oscillating pattern. This pattern kind of emerges in some kind of spontaneously. That's why it's called persistent spin helix. From the theoretical point of view, this kind of experiments for spin propagation, spin diffusion, are described using the spin diffusion equation. It is shown here. So here S is a spin distribution in space, and this looks basically like a usual diffusion equation, except for one thing. Here in the spatial derivative top, there is an additional contribution, this lambda, which are the matrices, skew-symmetric matrices 3 by 3, which affect on this spin polarization S. So they describe spin rotation in spin orbit field. So when this lambda acts on spin, it rotates the spin vector around the corresponding direction, the direction corresponding to the motion. And this form of the spin diffusion equation suggests that this lambda can be interpreted as a sort of gauge field. In this case, we consider S as a usual vector, and that's why it is an SO3 gauge field. Then, in general case, when alpha is not equal to beta, lambda x and, I'm sorry, here it should be lambda y. Lambda x and lambda y correspond to rotation around different directions. They do not commute with each other, and this gauge field is non-abelian. One can assign a kind of strength to this gauge field, which is just a commutator. It's non-zero, and this means essentially that the spin relaxation is present in the system. However, in this special case of persistent spin helix, one of the components of this gauge field vanishes, lambda x vanishes, and then we have only one component. Obviously, then this gauge field is abelian. One can just eliminate it by gauge transform, by multiplying the spin distribution by this spatial dependent rotation matrix. And in then this eliminates the gauge field completely from the diffusion equation. We have a usual diffusion equation, and the thing we know about the diffusion equation is that the homogeneous distribution doesn't relax. It doesn't diffuse, nothing happens with this. So this homogeneous distribution has infinite lifetime. The homogeneous distribution is S tilde. But if we transform back to our original variable S by a spatial dependent rotation, we obtain this oscillating spin pattern, which also doesn't relax in this idealistic case. So this is a little bit theoretical. In practice, what is needed to do is we just need to solve this spin diffusion equation, and this can be done most conveniently by finding the eigenmodes, which are, in case of infinite homogeneous system, just a kind of spin waves, oscillating spin patterns, like here. We can find for each Fourier harmonic of the spin distribution, which is characterized by wave vectors Qx and Qy, we can find the corresponding relaxation rate, and then we find that this relaxation rate has minima as a function of qx and qy, and this minima is what determines spin dynamics at large times. So if we start from whatever spin distribution, we can decompose it into the Fourier integral, and then all the Fourier components will relax, and at large times, the only thing is remains are those modes with the lowest relaxation rate. And that's why it doesn't really matter from what spin distribution we start. With time, always the same spin pattern arises, corresponding to this persistent spin helix. Okay. This was the first approach to suppress spin relaxation, and now I will move to the second one. And it consists in limiting electron motion to a quasi one-dimensional channel, similar to shown here. So we have a channel of width W, and the crucial thing here is that the width of this channel is much smaller than the spin precession length, that is the length at which spin of electron does a full turn. So this doesn't have to be a quantum channel, there shouldn't be a quantization in the transverse direction, it's still two-dimensional diffusion, it's just that this channel should be narrow enough in practice, around few microns. So what happens then? Then when moving across the channel, the spin rotation is weak, it's by a small angle, and this small rotation, they effectively commute with each other and cancel each other. Whereas when moving along the channel, we can accumulate a large rotation, and this rotation persists. In the end, we have a simulation somewhat similar to this persistent spin helix regime. We have effectively a motion only in one direction and the spin rotation corresponding to it. So if we again look at the kind of Brownian motion on the Bloch sphere corresponding to a channel, we will find the situation like shown here. So on the Bloch sphere, the motion, the diffusion of the spin vector is limited to a belt, and the width of this belt is determined by the ratio of the width of the channel and the spin orbit precession length. And again, effectively similar to the persistent spin helix, rotation occurs almost only around the same direction. And then, similar to the previous regime, the spatial oscillations of spin polarization arise, and one can find what is the lifetime of these oscillations. It is determined by this expression, and the crucial thing here that it depends on the channel width W squared. So when the channel width is decreased, this spin relaxation is suppressed. And this was indeed observed in several experiments. It was shown that when we decrease the channel width from some microscope, from tens of microns to a few microns, the decay rate is suppressed at least by an order of magnitude. Okay, and finally I come to original results. So what I'm going to speak about is the way how to suppress spin relaxation without limiting spin transport just to a single direction, and at the same time which doesn't require this fine-tuning of spin orbit parameters which is required for persistent spin helix regime. And what I propose to use is a grid-like structure shown here. So here I show a grid made of narrow channels, the channels similar to what I described on the previous slide. So now we arranged them in this square grid. In this square grid, electron can still move in any direction, but its motion is limited to this grid. Okay, and this upper panel shows the evolution of the spin distribution in this grid, similar to this experiment that I was describing, but now it's calculated from the spin diffusion equation. So initially we excite spin polarization in the center, and then it spreads in the grid further and further with time, and the spin oscillations appear. This kind of checkerboard pattern appears of alternating spin ups and spin down. This is somewhat similar actually to what is observed without the grid. So if we remove a grid and consider spin diffusion in the free electron gas, a similar situation happens. So we start with spin up, then an oscillations in space appear. But the crucial point that the lifetime of the spin distribution in case of the grid is much larger than the lifetime without the grid. So the grid doesn't restrict spin diffusion effect. The effective diffusion coefficient, the spread of the distribution in the grid and without the grid is basically the same, but the spin relaxation is drastically suppressed in the grid. And now I'm going to describe how that works. Yes, before I move, I just want to know that this particular figure was calculated for pure Rashba field, but essentially it doesn't matter. Similar situation can be realized for other spin orbit field configurations. Okay, so in order to describe theoretically spin diffusion in such grid, the natural description is in terms of block modes. So we again, similar to case of free electron gas, we try to find eigenmodes, but now since the structure is periodic in space, we need to consider a unit cell of the structure, then impose periodic boundary condition with some quasi-y vectors, and then find these eigenmodes and find their decay rates. And this plot shows the decay rate of the mode, of the block mode, as a function of its weight vector, Qx and Qy. This is somewhat similar to dispersion of electrons in a superlattice. The only difference that here it is not the energy which changes with Qx and Qy, but the relaxation rate. But essentially, it's all the same. You can see here three surfaces. They correspond to three spin modes with orthogonal spin polarizations. And you can also see that there are minima which are marked by these circles. These are the most long-lived modes, those which determine the spin dynamics at large times. And the calculation shows that the spin relaxation rate corresponding to these modes is as small as for a channel. So my grid structure doesn't introduce additional spin relaxation as compared to the channel, but it allows the electron distribution to be transported in any in-plane direction. As I mentioned, this first calculation of the spin diffusion in the grid that I shown, it was done for the case of pure Rashba field, but it can be repeated for any spin orbit parameters, and the parameter which actually matter for the consideration is the ratio of the period of the grid A to the spin precession length, lambda x and lambda y. So lambda x and lambda y are the precession lengths for the spins moving along x and spins moving along y. In case when we have both Rashba and Wesselhaus terms, we can have different values of lambda x and lambda y. And here it is the dependence of the relaxation rate of the most long-lived mode as a function of these spin orbit parameters. The change of alpha and beta correspond to moving along these diagonals, and these are just along the main axis are just more natural parameters, a over lambda x, a over lambda y. And now you can see that the longest lifetime, the smallest relaxation rate, is achieved not only in the persistent spin helix regime. So persistent spin helix regime, it is the regime marked with dashed lines. It corresponds to alpha and beta of equal strength. But in addition to this minima, which was even in the absence of the grid, a series of additional minima arise, which form this kind of also grid here. And this kind of resonant condition for the spin relaxation to be suppressed is that a over lambda x or a over lambda y should be integer of half integer. So if this kind of resonant condition is fulfilled, then the spin relaxation turns out to be suppressed. On the right, I show a few spin distributions corresponding to the most long-lived mode. This first one is this checkerboard pattern that I has already considered, but a different long-lived modes also exist. There are modes where spin oscillates only in one direction, or there are modes where the pattern is even more complicated. But essential thing that for all these long-lived modes, if you decrease the width of the channel that forms the edges of the grid, the spin relaxation scales to zero in theory. So the mode decay rate as a function of the channel width scales to zero when I decrease W. Of course, in the reality, there are other mechanisms which limit it, but I'm not going to consider them now. And now, so we have seen that under certain conditions, this kind of persistent spin grid occurs in the sense that there is spin distribution of the grid, and in the limit of narrow channels, the lifetime of this spin distribution diverges. And now I want to formulate the condition, kind of recipe, that can be used for any kind of lattice to determine the parameters required to have this persistent spin grid. And this is done quite simply. So we can consider any kind of lattice. For example, here I draw a hexagonal lattice, and we consider electron diffusion around a placket of the grid. As electron goes around the placket of the grid, its spin rotates by a certain angle. And this rotation matrix can be formally written in this form via this gauge field lambda that I introduced in the beginning. So, and essentially this is what is similar to the Wilson loop in lattice gauge theories. So we take this rotation matrix and we consider spin diffusion, spin propagation in the grid. So if this rotation matrix is just any matrix, then by going around one placket, then adjusting another placket, we can obtain all different sorts of rotation. However, a special situation happens if the rotation matrix reduces to identity. If going around the placket no rotation happens to a spin, then going around any number of plackets also gives no rotation, and effectively we don't have this diagonal spin relaxation mechanism which originates from the electrons moving along different paths and exhibiting different rotation. Here, similar to this persistent spin helix regime, irrespective of the path that electron moves on the grid now, the spin rotation is always the same. And this, therefore, is the essential condition. If we want to have persistent spin distribution in the grid, we need to tune the grid parameters in such a way that this spin rotation matrix reduces to identity. And this is in some sense alternative to this tuning of spin orbit parameters. In this case, we don't need to tune spin orbit parameters. We can take whatever spin orbit parameters are in the structure, but instead we can fabricate a grid with a particular geometry which satisfies this condition. So this is the example, again for this hexagonal lattice. I calculated the spin rotation matrix R, and then from it I calculated the spin rotation angle phi. To be more precise, here I plot the cosine phi as a function of A over lambda x and A over lambda y. That is the ratio of the period of the grid and spin orbit parameters. And when the cosine phi is equal to 1, the rotation matrix reduces to identity, and this is the condition of this persistent spin grid. This condition is marked by these black lines and by black dots. There are several of them. This is just the cosine of rotation, spin rotation under the round trip for the placket. And here it is the calculated spin decay rate, and you can see that they correspond one to the other. Indeed, when the cosine phi is equal to 1, for example, for for this cross, yeah, you can see that in the corresponding point of the spin decay rate map, you have the minimum. So this method, it indeed allows to determine the condition when spin decay rate is suppressed. And on the right, I show this long-lived spin distribution corresponding to these two crosses. You can see that this kind of patterns appear in space. In this case, these patterns are commensurate with the period of the lattice. But in fact, if you choose some other point on this line, for example, it doesn't have to be commensurate with the lattice. It can have a different period. So, okay, this is one application of this grid. So using the grids, you can suppress spin relaxation. And other interesting thing which can happen is shown here. So we can think about this spin diffusion on the grid in terms of that it is kind of emulating of motion of some particle in a gauge field. In our case, in an SO3 gauge field. So if the spin rotation matrix R reduces to identity, then this gauge field vanishes. And if it is not identity, then there is some finite value of gauge field. And this strength of gauge field, you can think about it as a log of rotation matrix. Okay, and a few interesting configurations that can be achieved are shown here. On the left, I show the case with the, again, square grid, but now the size of a placket changes from left to right, it increases. In the center, the placket size corresponds to R equal to identity. However, on the left and on the right, it is different. One can think about it in the following way. So in the center, R is equal to identity, that means there is no gauge field. But on the left and on the right, there is a gauge field and of opposite direction. So this is a kind of domain wall between the regions of magnetic field, effective magnetic field of different direction. And then what can be expected in such structure that at the boundary with these two regions, an edge state should exist. And indeed, if we consider spin diffusion in such a grid, and at large times this kind of spin pattern appears, it is localized near this domain wall. And the idea behind it that this spin distribution basically corresponds to wave function of the ground state of a particle in this gauge field, because the spin diffusion equation is basically the Schrödinger equation in imaginary time. So at large time, spin diffusion reveals the most long-lived mode, that is the ground state of the corresponding Schrödinger equation. And on the right, there is another example, a gauge vortex, where the size of all plackets is the same and corresponds to R equal to identity. However, one central placket has a different shape. It can corresponds to non-identical R. Then for any path on this grid that doesn't enclose the center, we have no spin rotation, but for any path that doesn't close the center, we have some non-trivial spin rotation. This is a gauge vortex, and again you can find the most long-lived state, and it will correspond to the ground state of a particle in the gauge field with this kind of gauge vortex. And in the end of my talk, I want to discuss a little kind of topological properties of these grids. So I introduced the spin rotation angle. So when going around the placket, spin exhibits some rotation described by this matrix R. And you can also think it in the following way. So you go around the placket, and at the same time you see what rotation it has already exhibited by the spin. So you can think about this R as a function of the path L around the placket. So L changes from 0 to the full trip around the placket. So we start with no rotation, we do the full trip, and we come to some different rotation. And in case of this persistent spin grid, this final rotation is also an identity. It's also no rotation. So what actually happens here, we have a map from this loop path in the real space to a loop path in the SO3 group. And the interesting thing about SO3 group is that it is not simply connected. That is, all loops in the SO3 group can be either trivial or non-trivial. And this distinguishes two classes of these persistent spin grids. And to reveal to which class some particular spin grid belongs, one needs to lift this path in the SO3 group to the path in the covering group, which is SO2 group. This is from mathematical point of view. From the physical point of view, what happens with this lifting is very straightforward. So instead of considering rotation of a spin vector, we consider rotation of a spinor. So we have a spinor which is rotated basically in the same spin-orbit magnetic field, and when we do the round trip around the placket, we know that the spin direction hasn't changed. But this means that the spinor has either remained the same or has flipped the sign. And these are two different configurations, two non-equivalent configurations, two classes of these persistent spin grids. And if we do this lifting, consider the rotation of the spinor. This rotation is shown here. Here is shown its cosine of phi over 2. So when it is either 1 or minus 1, this corresponds to a full rotation of the spin vector. But you can see that on these lines, the spinor keeps the sign after the round trip. And for these dots, which also correspond to the same spin direction, the spinor actually flips the sign. So these lines and dots actually belong to different classes. But for everything that I was talking about concerning spin dynamics, this actually has absolutely no effect. Both these classes of spin orbits, of persistent spin grids, behave in exactly the same way. This is almost the end of my talk. So I first summarize the results and then say a few words as an outlook. So the main idea of this work is that we propose a kind of additional mechanism to suppress spin relaxation, that is to impose on the structure a grid with a certain period chosen in such a way to satisfy this condition that after going around a trip around the placket we have no spin rotation. If we do this, we have a suppressed spin relaxation. And I believe that in principle this can be done. This is the theoretical work, but in principle this can be done in practice because the channels are already quite easily fabricated by etching of the quantum well structure. In principle, there is no obstacles to also by etching perform this kind of grid structures. And as an outlook, I want to mention, so I said that these two topologically distinct classes of persistent spin grids do not show different properties in terms of spin diffusion, but actually we have considered quantum transport in the same kind of grids, that is the conductivity of the grid. And we show that for conductivity, this is indeed matters. Here I show the conductivity of the grid, again as a function of spin orbit parameters. And this first plot, it is shown in the diffusivity regime, and then the quantum correction to the conductivity is due to weak localization or weak anti-localization. And then again, the two classes of the persistent spin grids, trivial and not trivial, this correspond to these lines or this center. They manifest exactly the same properties. However, if we go to the quantum regime of ballistic transport, then we see that the value of relativity in the center and in this square, in the center and the square, is different. That is, the conductivity of the grids in the quantum regime indeed feels the difference between the classes. That is, this geometrical phase accumulated of the spinor when going around the planet. So that's all. Thank you for your attention.
Thank you.